Hello class, welcome to 4.7, Exponential and Logarithmic Models. As the name says, it's about modeling your real life situation that's presented in the problem by using either exponential or logarithmic functions. So in mathematical modeling, we use familiar functions so that we could kind of model the real world phenomenon that we wish to analyze. So you can think of exponential and here it's rapid growth, right? So we think when we talk about exponential, let me just write here growth, because you could also have exponential decay. So I'll just write exponential growth. Here we use the function y equals a naught e power kt. If you see this clearly, more deeply, you can see that this is nothing but y equals, or remember the PERT formula? So let me put that format. A equals PE power RT. We use this in compound interest, and we modified the compound interest formula for continuous compounding using this, right? In this, the players have changed. A is now Y, P is A naught, initial value, and R is your K. All others remain the same, right? So this is basically a PERT formula, and that is your basis for exponential growth function. And to define these values, A naught represents the value at time 0. That's why it's A naught, right? Say the initial value. E is that constant we know, Euler's constant. And of course, K is the rate of growth, right? Because it's the rate of growth, it will be positive. And Y, of course, will be the end result, after the growth has taken place. So we also use exponential growth for understanding, especially applications that involve doubling time. Doubling time or double time, okay? That is the time it takes for a quantity to double. The most popular example for this would be the growth of a virus, the growth of a bacteria. Now with the coronavirus situation, you can actually see how meaningful these things will be for us to begin to apply or see the application of these functions in real life situation, in situation that's unfolding right now. So to first determine if it's an epidemic, they have to make sure that it has multiplied in a certain speed, and then to make sure that that is now going to be an epidemic, meaning it's going to spread fast. Again, they have other robust measures to see the speed of growth, or in this case, the rate of growth, right, the percentage. And so natural resources usually exhibit that kind of growth, and so it's usually based on doubling time. So you can't wait for it to if you want to test something for 24 hours, yes, of course we do that. But if you want to kind of quicken that experimentation, you can use the doubling time to see how long it takes for it to double. If it takes 24 hours for it to double, yes, that's the time then it takes. But if you're just observing for 24 hours, that alone does not give you all the details we need, right? Because we don't clearly see the rate of growth. So doubling time is a very commonly used application when it comes to natural resources. All right. Then you know about exponential growth. Remember, I gave you the hint of plane takeoff and plane landing. So if the plane takes off, that is your exponential growth. It's rapid growth, we know that, right? And we always want to make sure that we are remembering the right shape, okay? Because if you change the shape, the direction, or you know, even if you wrongly flip it, we've lost the growth pattern then, right? So let's remember that, that it can involve very large or very small numbers. Then we have something called order of magnitude. So it is usually the power of 10, right? Order of magnitude is measured because our base is 10. It's the power of 10. Where have we seen this? Well, we've seen this in scientific notation. For instance, let's say the distance to the nearest star, right? Proxima Centauri, that's the nearest star. Distance is given to be, is measured in kilometers. So the distance is, I really can't even read this, okay? So I'm just going to write this, 40,113,497, 200,000 kilometers. See that's a mouthful, right? Now, if you were to use scientific notation, right? Scientific notation for this would help us to make it more manageable. So what we do is we move the decimal point, if you remember the concept, to shrink this number to a number between 1 and 10, rather I should say, yeah. And then adjust that shrinking by using the order of magnitude. So what happens here is I'm bringing this decimal point between 4 and 0. So 0, 1, 1, 3, 4, 9, 7, 2. And you don't really need to have those trailing zeros, right? Because you put the decimal point here. And then count the number of spots you moved to get here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You moved 13 spots. So it's 10 power 13. And that helps us to actually see that 13 more visibly, right? And understand how big it is. And the order of magnitude here is the order of magnitude of 10 power 13. So you have expressed a very large number in a manageable manner by using the order of magnitude. You could do likewise for a very small number, and you could move the decimal point in the other direction to bring it to a number between 1 and 10, not 10 not included, of course. And then you could then use the 10 power negative number because you moved in the opposite direction to express the order of magnitude there. But we usually are talking about the positive order of magnitude here. So let's take a look at the first question. A research student is working with a culture of bacteria that grows at a rate expressed by f of t equals 1550 e power 0.0256 t, where t is in minutes. There are two parts to this. One, to the nearest whole number, what is the population size after 30 minutes? And two, find the time when the population will be 10 times its initial value, rounded to the nearest minute. This is similar to what I was talking about, the doubling time, right? So you can wait for 24 hours and see what was the population size, right, after 24 hours. Or you could, say, what time does it take for this to double? So a similar thing. So you can give the time and ask what the size would be, or you could give the size and ask what time will it take to reach that size. So let's work on this problem. So for the first part, okay, this is kind of simple to solve because they gave us the time. Right? So let's say f of t is given to be 1550 e power 0.0256. 0 256. You know how costly that will be if I start at 0. And we're told that time is 30 minutes. Now, t is measured in minutes, so no conversion required. If they gave us, say, to the nearest whole number, what is the population size after half an hour? Then it is measured in hour, so half an hour has to be converted to 30 minutes, and then you would resume with the problem. So plug in t as 30. That's what makes it a simple problem. Times 30. So plug that in, use your calculator. So it should look something like this if you are doing step by step in the calculator. If you're entering them all in one shot, make sure that you use parentheses and you raise them to the power correctly and all that. Make sure that the format is right. And they said round to the nearest whole number because you're counting the number of bacteria, so you don't want any decimal answers there. So then you will say, there will be, this is word problem, so please go back and interpret your answer, because I did not say what 3341 is. It is 3341 bacteria, right? So there will be 3,341 bacteria after 30 minutes. And for question number 2, it was the other way around. So what will the population be, or they're asked when the population will be 10 times its original value, its initial value. Let's write the general form. The general form we wrote earlier, right? Y equals A naught. So instead of Y, I'm just saying f of x, because we're going to plug in for x, or we need to solve for f of x. So we need to figure out what that is. E power kx. So A naught is the initial value, and here A naught is 1550, right? We're writing the format first so that we can detect what the initial value is. Because they didn't give us the initial value explicitly, it is included as part of the equation they gave us. So we kind of look at it in its general form to identify the individual values. So if we are asked to find what the population size will be, I mean, what time it will take for the population to get double its, I'm so sorry, I'm stuck on the double. If the population will be 10 times its original value, population, I will say new population, okay? New population will be 10 times the initial population, so 10 times 1550. And this would be your f of x, right? Because f of x stands for the new population, isn't it? And if you're not happy with the x, like if you wanted to keep it as a t because t represented the time, and you didn't want to change the variables, because I just made it x so that it's like a regular equation in y and x. But if you wanted it to be in t, then the same thing, I'll just write it here, the same thing will look like this, f of t equals a naught e power kt. So you're totally fine in keeping that. In fact, I would recommend that. I've just followed the book, so I just used the x. If you keep it as t, then it's a lot easier because you're looking for that t. All right. So the new population, the accumulated value, f of x, is your 10 times 15,550. So f of x equals a naught, 1550, e power, k was given to be, so you go back to the original equation, right? 0.0256 t, or x. You could use x or t here. I'll just keep it as t. And you're trying to solve for t. So t is sitting up in the power. So it's not as straightforward as the previous question. So 10 equals e power 0.0256 t. And you kind of have to use logarithmic application here. So you need to apply log in order to So bring the t down. And here, because of the e as the base, you want to use natural log. So I'll say apply natural log on both sides. You're welcome to use the formula, the conversion formula, to also approach this answer. So we have ln10 equals lne 0.0256t. And we know that this really enables us to bring the power down to the front. So ln10 equals 0.0256t lne, and we know that lne is equal to 1, so that makes it even better. ln10 equals 0.20256t. Then one last step, get t by itself. And so t would be ln10 over 0.0256, which is approximately 90. So remember, t is measured in minutes. So after 90 minutes, the population of bacteria would have grown to 10 times its initial value. And that's what you're going to write now. Again, remember that I did not attach the units to the t. So when you interpret, that's when you bring the minutes. After 90 minutes, the population of bacteria will have reached 10 times its initial value. Okay. So now let's go to the next problem. A biologist observed a population of bacteria that grew at a rate expressed by this. It's an exponential expression. T is measured in minutes. How long will it take for the population to reach 8 times its initial value? Very, very similar to the previous one. So recall that we first write this in the general form. So A naught e power kt. And so you can see that A naught is 358. That's what we wanted to see explicitly. And of course, E is 0.0425. The question says how long. That means you're looking for t. What is t? So you want to solve for t. Means the future value, okay, f of t, is the population, right? It's the population, or the new population, I should say. So the new population is 8 times 358. I don't want to multiply it because I know I'm going to use it to reduce it. So 8 times 358 equals 358 e power 0.0425t. Right? That was the given expression. You kind of plugged in for f of t as 8 times 358. That was given to us. And then go ahead, proceed with the simplification. And then apply ln. ln 8 is lne power 0. You bring the power down, and all that reduces to 0.0425t. And one last step to get t by itself. Oops. And that is approximately 49. I will let you complete the sentence for this. but I will just verbally mention this. After 49 minutes, the population of bacteria will have reached 8 times its initial value. Now let's talk about exponential decay. This was exponential growth. As we can very well recall, exponential decay is kind of marked by your graph coming down like a plane landing, right? Growth was takeoff, this is plane landing. And so we'll mark this as exponential decay. And you notice that the formula for this also is the same as the other one, y equals a naught e power kt. And a naught, of course, is initial value, initial population, or the population at time 0. And k here, because it's the rate of not growth, but rate of decay, k will be negative. And you can see that your y, or we might use f of t or f of x, depending on how we want to present it, that will be the new population again. From the initial population, that's a new population, but this time it's decay, so it's going to reduce, it's going to become less. So the prominent application that we use here would be half-life, okay? In exponential growth, double life or doubling time is what we would be interested in. Here, half-life would be to determine how long it takes for it to reduce to half its original quantity. I'll just say time taken to decay to half its original quantity. Remember, it's not a slow decay, it's an exponential decay. So it's going to happen quickly. Again, quickly is also subjective, but you can understand what I mean, right? So it's the time that's taken to exponentially decay to half its original quantity. So when you are, say, trying to find y, have the understanding that your y value should be less than your a naught. It should be less than the initial population if you're talking about decay. If you're talking about growth, your y, which is the new population, must be bigger than your initial population. Okay? Okay. Half-life, double life, we'll talk about that quickly. Okay. When we specifically say double life, okay, then we are already saying how it grows, right? We're not saying it 10 times or 8 times, we're saying 2 times. So in this case, it'll be 2 times your initial value. So 2 times a naught will be a naught e power kt, right? So this will be your new population. The new population is 2 times the original population. And when we talk about half-life, that will be half of the original population. That is your new population. So your equations will be set up like this. Remember, the players are still the same, but then the way you set them up has changed. So for double life, your new population, the y, is 2 times a naught. For half-life, the new population y is half a naught. And also remember that for in here, your k is positive for growth, and your k is negative. And if you wanted to, you can always use this general format to derive the half-life formula. So in this half-life formula, Okay, I'll quickly show that side or that derivation here. If you wanted to solve for t, you get the half-life formula. So sometimes your exercises will give you this formula right away and begin calculating. And so if you're wondering where this came from, it came right from this expression. So I will derive this here. Divide both sides by a naught. Remember, you're trying to solve for t, so you want to get t by itself. So this is half equals e power kt. Then apply ln. Ln half equals ln e power kt. Now ln half is actually ln 0.5, but we're not going to do that. We can simplify this even further if we did the quotient rule. So if you did ln1 minus ln2, right, quotient, numerator minus the denominator, then this would be kt ln e. And then if you come back here, ln1 is 0, ln e is 1. So that will kind of reduce it for us as negative ln2 equals kt, and one more step and you got your t by itself. So this would be the formula that sometimes that problems can use this formula, or explanation can be given to you directly by using this formula. Okay? And if you don't have to know this formula, you can still do that. What you have to know is how you set up the initial equation, half a naught on the left for half-life and twice a naught for the new population. You can also derive a similar formula for half-life for t. Okay? So we'll look at a problem now. The half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time. Then determine how long it will take for the amount of carbon-14 to reach 40% of its original amount, rounded to the closest year. All right, let's take it one step at a time. They have given us the half-life to be 5,730 years. Okay, half-life is that. But before that, they said express the amount of the carbon-14 remaining as a function of time. Okay. So then once we find that function, and then we will be able to use that function to do the last part. Okay. So the half-life of carbon is 5,730. Okay. Remember, half-life is the time taken for it to become half the original value. So let me first write the formula here. Y equals a naught e power kt, isn't it? And because they use the word half-life, you know this is to do with decay. Half-life implies exponential decay. And if it's exponential decay, your k must be negative, right? Well, we're trying to find what k would be to rewrite the formula in general, right, like this. But we need to plug in for a naught, we need to plug in for k, and then the function will be in y and t, right? So let's get started on that. We are already told that the half-life is the time, right? So which implies t is 5,730, half-life is the time. And now we have to understand again that half-life indicates that y, let me write it here, y is half of a naught, half the life. So y is half of a naught. Let's plug that in there. We don't know what a naught is. K times 5,730. Now, if we solve for k, then we could plug that back in the equation and give a general function of time, right? So it's okay if we don't know what a naught is, because it's going to get canceled off anyway. So I'm trying to derive this. I'm not using the shortcut formula. The formula, look at this one, the t formula that we did here. because you could use that t formula and just switch it for k. So k will be negative ln2 over t. So you can directly do that, no problem. Just for practice, it's good to solve it when we have the time. So, we took ln half. Because you're deriving, I want to give you the option, the alternative, to also see it as 0.5. What if you didn't want to do the quotient method to get the negative? It's totally fine because half terminates with 0.5, a terminating decimal number. If it doesn't terminate, we do not recommend that you change it to a decimal. Okay. What you saw here, let me quickly take you back here. What you saw here was if you solve this for k, right? If I solve this for k, I would get negative ln2 over t, isn't it? And k should be negative because this is exponential decay. So you can see the negative explicitly when you took the quotient rule to split up the half as 1 and 2, ln1 minus ln2. But if you're keeping it as 0.5, you won't see the negative. But if you took your calculator and found what ln2 was, I'm sorry, ln 0.5 is, I'm using the calculator as well. It gives you a negative quantity. It says negative 0.693147, etc. So you know that the negative is inbuilt there. You just can't see it explicitly. So if you're using this, be aware of that fact. So ln half equals 5730k, and then you solve for k in one last step. So k is ln 0.5 divided by 5730. Now, if you wanted to use the formula, if you use the formula k equals negative ln2 over t, then you would have a negative ln2 over 5730. They are equivalent, okay? Again, if you're not convinced, go ahead and find out what ln2 is. ln2 would be positive 0.6931. So with a negative in front of it, you have a negative 0.6931, which was your ln 0.5. So they all will have to be the same in the end. So we got this. All right, now come back to the format. Okay, so I'm going to bring that here. Y equals a naught e power kt. So that's what they wanted us to write with the k. Right? So the y can be written now as f of t because they wanted it to be written as a function of time. So f of t is a naught e power, k was just found to be ln 0.5 divided by 5730 t. We still don't know what a naught is, but this is an exponential decay function, decaying continuously, right? Because of the e, it's a continuous decay. All right, now let's go back to the question, and as the last part, determine how long it will take for the amount of carbon-14 to reach 40% of its original amount, rounded to the closest year. Again, we don't know what the original amount is, but it's all spoken in reference to the original amount. So we can use that information here. So your original amount is A naught. Let me just box this so that we'll use that in this upcoming part. Initial amount is A naught. This implies new amount or new population, right, is 40% of this. So it's 0.4 A naught, 40% of initial population. So it's 0.4 A naught. Now you can plug this in your f of t. F of t is now 0.4 A naught, which is equal to A naught e power ln 0.5 over 5730 t. Okay. All right, go ahead and solve. We're trying to solve for t, right? So you want to get t by itself. 0.4 equals e power then apply natural log on both sides. And ln 0.4 equals, the whole thing comes down. That's ln 0.5 over 5730t. ln e is 1, so we're skipping that. And then one last step. This looks bulky, but we're going to use the calculator shortly to get that. We have to be careful because this is a complex fraction. So just to help us, I flip the denominator. So if you're using the calculator all in one shot, then remember to put the denominator in parentheses. Okay? But if you are taking it one step at a time, then you would present it like this. Either ways, your t upon using the calculator comes out to be 7575. Okay? They wanted us to round to the nearest year. Come back and see this was all about half-life. So it's a decay. So 5730 was the original or initial, no, was the half time, sorry. So that was a half time, t was a half time. So if t was a half time, then that was the time that you're finding now, right? Yeah. It's all decaying. So if it's now 40%, there it was half of it, here it's 40%. So you should see that the decay is reflected here. Then let me write the definition here. I'm sorry, the interpretation here. It will take approximately 7575 years for the amount of carbon-14 to reach 40% of its original levels. If you think about this, this makes perfect sense because for something as old as this, we really don't know what the original levels would have been. And this approach helps us to overcome that limitation because in all these places, your A naught, we don't know what A naught is, the initial level, but your A naughts will get canceled off in the process. So it's okay if you didn't know A naught because what really matters is that you had the time, the half-life time that you were able to start with, 5730 years. Okay. All right, so about that. We'll do a similar problem now. CCM137 has a half-life of about 30 years. Given this half-life, we can represent its decay as A equals A naught e power ln 0.5 over 30 times t. If we begin with 400 milligrams of CCM, how long will it take for it to decay to the point where there is only 2 milligrams remaining? Round to the closest year. Okay. A equals A naught e power ln 0.5 over 30 t. And they've given us that the initial, right, we begin with So you know this language here tells you that it's the initial A naught. And how long will it take? How long is finding T, where it's decayed to the point where only 2 milligram is remaining. This is the new population, right? So this is your A. I've given you a variation here. I've used, in this equation, in the problem, they didn't use Y, but they used the capital A with no suffix. So A is the new population, the new amount. A naught is the initial amount. A is the new amount. So make sure you use the corresponding letters because they all mean the same thing. They're just represented differently. So we got all of these. So your A is 2. And also note that 400 is also measured in milligrams and the remaining amount is also measured in milligrams. So we're good here. Otherwise, we have to do the conversion. So we started with 400 milligrams, but it's now reduced to 2. So E power ln 0.5 over 30 times T. All right, now it's time to do the math part. 400 divided by 400. That's what's swapping. Let's get that. So it's 1 over 200. Times T. All right, apply your ln. Ln 1 over 200 actually would become negative ln 200, right? But remember, we are trying to use the calculator, so you don't have to calculate ahead of time. Wait till the last step, and then you could send them all to the calculator. And then divide both sides by. And then the T is negative ln 200. If you didn't figure it out as negative ln 200, no worries. Leave it as ln 1 over 200 because your calculator will take care of that. Divided by 30. And that gives you approximately 229 years. Yeah, and I leave the explanation, the interpretation. We've rounded it to the closest year, so that's it. Let's focus on logarithmic models. So far we saw exponential models. So we saw one for the models for exponential growth and exponential decay. So here we look at logarithmic models. Again, where do we use logarithm in real life? We use it as a measuring scale, right? When we talk about power gains, audio gain, sound pressure, earthquake intensity, pH level, and so on. I'll just quickly write that stuff here. So earthquake intensity. You know, to measure decibels. So for sound pressure maybe. In chemistry, we use it for pH. All right. Because of the logarithmic scales, they are useful to when the value is being measured across different orders of magnitude, okay? Because it measures the magnitude. So when you have different powers for 10, right? Let me write order of magnitude. Comparison. So for example, if we talk about an earthquake with a magnitude of 4 on the Richter scale, so if you had another earthquake of magnitude 8, so let me just write that here, magnitude 4 and magnitude 8. Because in the background, the logarithmic models are measured by factors of 10, what you see here is magnitude, earthquake of magnitude 10, of magnitude 4 is 10,000 times weaker. This is 10,000 times weaker than magnitude 8. Okay. Why 10,000? Because you had the difference between them is 4, right? So it is 10 power 4. That is what is the difference. So we're able to compare them in a reasonable way like this, as opposed to dealing with very large numbers, because the order of magnitude is what you're using to compare. Okay? And when we talk about chemistry, pH scale, it's used to measure the acidity or alkalinity of a substance, right? And the pH, let's come over here, pH, this runs from 0 to 14. I recall water is exactly at 7, so water is the middle value, the balanced pH. Okay. All right, anything less than, so 0, let me put it as a scale maybe, easier that way. 0, I wanted to put the 0 here. 0 to 14 is the extent, and 7 is the middle point, right? So if it is here, then we call it, if it's less than 7, it's considered the solution, the substance is considered acidic. And if it is greater than 7, we call it alkaline. The substances are said to be alkaline. For instance, our bodies must have a pH, must maintain a pH level close to 7.35 to make sure that our enzymes work properly, right? So that's why they say don't skip your meals and all that, because then your stomach acid will begin to interfere, and so you'll feel acidic as well, right? And certain foods cause acidity, so that hinders digestion. So it's all in the background to do with pH maintenance. Here are some, ones that we have. The pH levels for some familiar stuff. Like for instance, battery acid is 0.8, stomach acid is 2.7. And notice that all these are less than pH level of 7, so they're acidic. Orange juice is 3.3, so it's acidic. Pure water is 7. Human blood is 7.35. That's why we should maintain that for the enzymes to work. Fresh coconut is 7.8. It's more than 7, so coconut drink is alkaline. Sodium hydroxide, lye, is 14. That's the extreme end there of alkalinity. Interesting. All right, we'll look at pH. Okay. The formula for that is negative log H plus. Okay. And I'll explain what that is. H plus is the concentration of hydrogen ion in the solution. So let's write that here. H plus is the concentration hydrogen ion in the solution measured in moles per liter. You can use capital M for that. So when we interpret our answer, we really want to make sure that we include the measurement. The unit of measure here is M, moles per liter. Okay, so here's the question. Coffee, my favorite, typically has a hydrogen concentration of 0.40, 2, 3, 4, followed by a 1, M for the moles per liter. What is its pH? So then you simply plug it in the formula. pH is negative log H plus. And we know what H plus was defined to be. It is the concentration of hydrogen ion. So that information is given to us, and it's measured in moles per liter. So we got negative log 0.40 followed by 1. That's a negative, and log of this decimal quantity will be a negative. So that's a negative 5 there actually. So it comes out to be 5. So pH is 5. Very interesting. I never thought coffee as being acidic. This is less than 7, right? That's the pH of coffee. But you know what? I drink my coffee with milk. So hopefully, because I don't like acidic stuff, so hopefully it has kind of diluted the acidity that pure coffee has. All right, what about salt water? If I said salt, what if I said, if the problem says salt water has a pH of 8.1, right? It's alkaline. What is the hydrogen concentration? So we could also do that. What, not why. What is the hydrogen concentration? So in this case, again, write your formula, negative log H plus. But remember, we're trying to find H plus. We already know what pH is. pH is given to be 8.1. Let's plug that in. Minus log H plus. Divide both sides by negative 1. It's like a small move, but that has to be done before you eliminate the log so that you could access H plus. So negative 8.1 equals log H plus. And think about it. This log does not have a base, right? There's no base. That means this is common log. And how do we eliminate common log? What will undo common log? The power 10, the base 10 will undo the common log. So raised to base 10 on both sides. So we have 10 power negative 8.1 equals 10 power log H plus. And you know, 10 and the power log will undo each other. So you get 10 power negative 8.1 equals your H plus. Okay. If you were to expand this, H plus, okay, it's negative power, so that means it has to be a very small quantity. Okay, and we have to kind of see how many zeros must go in before this, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. In fact, what I'm trying to do is I'm trying to plug this in my calculator. Let's see what happens here. So what I see in my calculator is 7.94328, something e power negative 9. So I'm going to just 1, 2, 3, 4, 5, 6, 7, 8, even 8. Just kind of rounding it there. Okay. So salt water has, and put your unit, of course, M for the moles per liter. So that's your salt water's hydrogen concentration. As you can see, it is so much better to write it in the order of magnitude as 10 power negative 8.1 as opposed to expanding it out because it's really too long and hard. Okay. What about rubbing alcohol? This has pH of 5.5. What is the hydrogen concentration? What is H plus? Same story, pH equals negative log H plus. pH is 5.5, negative log H plus. Then divide both sides by negative, so you get negative 5.5 equals log H plus. Then raise both sides to the base 10, so 10 power negative 5.5. Here 10 power log, so 10 and the log will undo each other, so you get H plus. So you can leave it like this, or you could pull out your calculator and try what 10 power negative 5.5 is. And you get 3.16277, etc., e power negative 6. Okay? Because it can't really write all the decimal places there for you, right? So this would be, let me write it here, H plus is, okay, so it is e power, okay, let me write how it appears in the calculator so you'll be able to interpret this. So 3.162277766, then it says e negative 6. What this is you have to interpret this as 3.162277766 times 10 power negative 6. That's what this means. This e is not the same as the small e, right? So that small e is the Euler's constant. This is not that. Okay. And if you were to put it in decimal form, you'll have to have 1, 2, 3, 4, 5. And the sixth position will be, because you have the decimal point here, right? So sixth position will be the 3.16227. M. Okay. Of course, you can round it, but you can clearly see that 10 power of negative 5.5 was so concise to for this case. So that's pretty much it. And if you had any data coordinates like this year, comma this population, this year, comma this population, you can use all that information additionally to the equation to deal with it as an exponential growth or exponential decay. But this pretty much is the idea on applications of exponential and logarithmic functions. I hope you enjoyed this video. I'll see you in the next one.